This is a video about applying Newton's second law. Newton's second law opens up all kinds of situations for us to analyze, which I'm sure you will find very exciting. This is how it works. You remember translational equilibrium? That's going to be our starting point. The big difference now is that we're going to replace the right side of our equation. With our translational equilibrium, we had this sum of forces equals 0. We're going to replace the right side of our equation with mass times acceleration. This means that a common thing for a problem like this is to solve for the acceleration. But sometimes the acceleration is of given value. In this case, I'm going to start off by working through a problem where we know the acceleration and use it to find an unknown force. Make it very familiar. We are standing. You are standing in an elevator car. And let's give you a mass of 50 kilograms. It's like 110 pounds, give or take. We're going to say this elevator car is accelerating upward at 2 meters per second squared. I'm going to start with a free body diagram because that's how these work. And what I would like to know is the normal force that the car exerts on my feet. On your feet. I've switched back and forth between who's in the car. It's you. I want to find the normal force on your feet. So you have become a dot. Sorry about that. Your downward force is mg. Your upward force is the normal force, and there is nothing else acting on you because all you're doing is standing on the ground. The whole elevator car is moving upward, but that cable isn't connected to you, so that tension doesn't show up. I'm going to have upward be my positive y direction, and there is my free body diagram. I'm going to label that this is a 50 kilogram mass. I think I'm also going to label that my acceleration is a positive 2 meters per second squared. Positive because it points upward, and I said upward was the positive direction. Here we go. Sum of forces. I have an upward force of N. That's the one I'm looking for. I have a downward force of mg, both of which values I know, so I'll put them not in red. And that is it for my sum of forces. Newton's second law says the sum of forces is equal to mass times acceleration, and I happen to know my acceleration this time. So I'm going to solve for n. I'm going to add mg to both sides. And I get n equals mg plus ma. I will leave a as not a vector in this sense because I'm going to plug in my positive, well, in this sense I'll leave it not as a vector because I'm going to plug in my positive 2 meters per second squared. I know that value. I'm even going to factor out this mass for a moment. So I get that my normal force is m times g plus a. Let me plug in some values. I get 50 kilograms times 10 meters per second squared plus 2 meters per second squared. That was what my acceleration was. 10 plus 2, that's 12, times 50 is 600 newtons. Is the normal force acting on your feet in this elevator that's accelerating upward. This normal force is the only force that's holding you up, and that, the total force holding you up, we call an apparent weight. And that's a term that you'll actually see quite a bit. It's the force that's stopping you from falling through the ground. is your apparent weight. If you were hanging onto a pull-up bar, just kind of hanging there, your apparent weight would be the tension in your arms. If you were standing on regular flat ground, the apparent weight's the normal force from the ground. If you are falling through the air, you have just jumped out of a plane and you are not you're not reaching a whole lot of air resistance yet or anything like that, you're just in free fall, your apparent weight is 0. In this case, your apparent weight is 600 newtons. Next part, same question, but now our elevator car is accelerating downward. So let's do that. Let's replace this with a downward acceleration. I'll replace this with a downward acceleration. The only thing that changes through this entire thing is that the acceleration, right, the vectors stay the same. The acceleration is just -2 meters per second squared now. So this will be a -2 meters per second squared instead of +2. 10 minus 2 is 8 times 500. That's going to be 400 newtons. And now your apparent weight is lower. If you were standing on flat ground, you would just get an apparent weight of your regular weight, which is going to be 500 newtons. So when we're accelerating upward, we get a higher apparent weight. When we're accelerating downward, we get a lower apparent weight, and you already know this. If you have been in an elevator, then you know that at the moment that you first start moving downward, you feel lighter for a second. Once you reach a constant descent speed, you have no acceleration, and now you're in translational equilibrium. So we are in that situation, plugging in right here, 0. 50 times 10, that's 500 newtons. When you get near the bottom of wherever it is you're going, the elevator slows. You're moving downward, so for it to slow, that means it has to have an upward acceleration. Your acceleration is positive. Now your apparent weight is more than your regular on-the-ground weight. That's how we handle Newton's second law. I'll do a separate video that does this for more dimensions and does more complicated cases, but for right now, that's it.